So 0.0288. So that's the amount of OCl minus divided by HOCl. So we could say that OCl minus is equal to it like that. All right, so that means if the total is 1.8 milligrams per liter, we now have a way to relate, the total we could then substitute in for essentially this equation. Now, normally, what we should do is convert the molecular weights so that we're not having any errors between, the 1.8 milligrams per liter of OCl minus is not 1.8 milligrams per liter of HOCl. If we were to fully convert that, there's going to be that slight error because the molecular weight is different, but it's pretty small. So I'm just going to say, let's leave that as a rounding error today. It's 51 versus 52, in terms of molecular weight. So we could just go ahead and say, all right, so then HOCl plus 0.0288 HOCl is equal to 1.8 milligrams per liter. So then our HOCl, what this will end up being is slightly less than the 1.8, right, when we solve for it. So that leaves us with 1.0288 HOCl equals 1.8 milligrams per liter. So we'll say that HOCl is 1.8 divided by 1.0. We could just do 1 plus that guy. So there we go. With the added error there, we get about 1.75 milligrams per liter. Okay, and that kind of makes sense that, at a slightly acidic pH, most of it is in HOCl. We know that. And so that kind of meets our expectations there. So over here then, let's go ahead and solve for the K. So K is equal to, well, let's say K times C is something we know from the data. Kc equals 0.3758. And now we know K is equal to 0.3758 divided by that concentration, 1.75 milligrams per liter. And this guy at the top was liters per milligram per second. And so what we'll get when we do this is the milligrams per liter will cancel and our K will be solved. So K then equals 0.3758 divided by this number. And this will be per second. So 0.215. And that then would be our final answer. Took a small shortcut, but we didn't take as big a shortcut as we could have if we just assumed that all of that 1.8 milligrams per liter was HOCl. A question? 2 questions.
So when you do the ln not equal to kct, which would give you your equation.
Yeah.
I guess I'm just curious why you get time in there instead of in then you're saying you're relating it back to the regular.
Like how we got from here to here.
I understand you're integrating to get there,
Uh-huh.
but like, so the final equation is y equals mx. You're just relating that right back to the original equation, even though you integrated to get to this one. Why would you have to do a thing until what you have to go back to the original equation to go relate it?
So what I'm doing is I'm relating this here. So
Yeah.
ln of n over n naught is y, and then this is m, and t is their x.
Is the x, not n, right?
Yeah, t is the x. So then when we take a look at the Excel, I plotted this, and I didn't label it, but this is it's a the x-axis is time, and so you see it's like 2 seconds, 4 seconds, 6 seconds. The y-axis is our natural log of the n over n naught. Does that make sense?
Yeah. Oh yeah. Okay. I'm thinking, okay, because we're not even using n.
Yeah, that's just into the y equation. Yeah.
Cool. Guess I'm just not weak.
Fair enough. I might not be either. Any other questions with this issue? Yeah. Yep, you're right. I did that backwards. Let's see. Got an answer. I'm not awake. Thank you. So this should be here per seconds. The overall, yeah, because the overall K star is the overall constant, and that's the overall picture is it's a first order decay, and that first order means that the overall rate constant should be per time units. What happened there? Okay. All right, so we're going to say liters per milligram second here. It works out still, and I think this part probably didn't work out the way I wrote it. So this would have been seconds to the -1, divide that by milligrams per liter. That leads us to this one. Yeah. Okay. That makes better sense. Yeah, thank you. Any other questions, issues? Okay. It is kind of neat to work with actual data like that. So hopefully if I were to put you in a lab and with some disinfection stuff, then you could find me some rate constants, or at least have an idea of how you'd go about that. Okay. So, ultraviolet light and UV disinfection. So I want to just come back and talk about UV stuff now. I know we touched on it before. Lots more we can talk about, and there's some stuff I might not get to today, but maybe we'll pick up some more tomorrow, or next time. Funny enough, in our syllabus, I was looking through it, kind of just checking on where we're at and stuff, and I realized this week was just gone from the syllabus, and I don't know why. It's just there was no week this week apparently, so I have fixed that, and now we have class this week. Surprise, surprise. Okay, so that's just to say we're on disinfection. We're on UV today. We'll be getting into advanced oxidation probably next time, but we might touch on a couple more UV topics if we decide that's interesting before we do that. Okay, so the UV spectrum, we're pretty familiar with the visible spectrum, and above that, in terms of wavelength, it's the infrared. I think we talked about this a little bit already. Essentially, what we're interested in terms of germicidal stuff is what we call UVC. And there are a couple new technologies, but traditionally, that's squeaky.
Sorry.
traditionally, the mercury vapor pressure lamps are what we've used. We have a low pressure one that emits very strongly at 254, medium pressure ones that are not quite as effective right at that 254 mark, although they do have that emissions peak, but they also have some extra kind of in higher wavelengths. So that's kind of the background, and then some new technologies. I've seen something about these plasmonic emitters that have something like a 222, which is kind of interesting. We'll talk about why maybe that's not actually that useful. Will depend. Then we're getting UV emitting LEDs that can do things more like 280 or 265, 305, different things like that, that may offer some benefits as well as the technology develops. So that's kind of the context here. Of course, if we get even shorter wavelengths, again, meaning like there's more waves hitting, so they're traveling, the photons are traveling at the same speed, right? The speed of light, but essentially how fast they wiggle, you could think of it. That says something about their energy level. Are they really chill, just infrared ones, or are they hyperactive, vacuum UV or X-ray radiation? If you go far enough past X-rays, we just start calling them gamma rays and stuff. So it's just the electromagnetic spectrum. So if you were to ever work in a biological lab, you've probably seen these in practice, kind of just right there in front of you, hopefully with a shield of some sort. They do a pretty good job disinfecting surfaces, so you just leave them on between experiments or something to help keep your surfaces as sterile as you can. I brought in the one as a demonstration the other day too for the bottle of water. Okay, so I think we probably also took a quick look at this. When we're looking at that germicidal effectiveness, essentially where DNA is absorbing light, because really DNA and that type of molecule is what we're targeting. If we can disrupt that replication, then we've inactivated or sterilized organisms so that they presumably cannot fix themselves and replicate. So again, that low pressure mercury, we have that large spike here. A medium pressure has kind of different emission spectra. And what I've heard about medium pressure is sometimes these other peaks may have some benefit in preventing microbes from regrowing, from repairing themselves. And that's a topic we might get into more next time, depending on how I'm feeling about what we want to cover. But essentially, they tend to be able to operate a little more energy efficient in terms of the disinfection they're providing if you have a large scale system. Normally, the low pressure, it just takes less infrastructure. It's for several reasons is kind of a little bit more standard, but for large applications, medium pressure can have a few advantages as well. So if we take a look at how we find these inactivation curves, what you want to do is use irradiation at different wavelengths, and we can use other light sources. We can use xenon lamps or other stuff to get different wavelengths. They're just not necessarily practical for actual application. So, for example, these ones were probably created with xenon lamps with UV cutoff filters so that light only in this window can make it through, and you expose your system. And it's an expensive lamp. It's fancy. It probably wears out quicker than the fluorescent ones, and it's kind of a lab scale test. So we can do some of this testing. We have the capability, even if we don't normally have the capability to select this carefully to apply in practice, or at least we haven't in the past. So what we see, a lot of organisms have a nice peak somewhere around 265. So DNA in general has that absorption, and in particular, it's the we'll see a thymine bond that is forming, and that it's whatever photoreaction that creates that dimerization is really what's, the molecules involved are absorbing this energy and absorb it most effectively at that wavelength. We can also see that if we do go down to lower wavelengths, perhaps we're getting some pretty good effectiveness depending on the species. So there is a bit of species dependent, but in general, this type of wavelength is what we call germicidal. It works pretty well. And so as we're designing UV processes, it is important to consider how susceptible a given organism is. Some may be easier than others. And then you want to design for your most difficult organism to kill. This applies to chlorine or other disinfection techniques as well, right? We want to be able to remove enough of the most difficult ones to achieve the disinfection. That builds in a safety factor, and then probably we go a little further and make sure that it's, we've done that much and maybe then some, right? So that's our typical design goals there. So a little bit closer of a look. I think we touched on it last time we talked about UV, but really what's happening in terms of direct UV damage, and this is a misnomer here. For direct damage, what we're looking at is these thymine reactions. So if we look on DNA, the different bases that exist and pair, that's kind of the genetic code stuff. If we have two of these thymine groups next to each other, which these would be the little bases next to each other, and we cross-link them by this this UV reaction, it's saying UVB. Generally, this one in particular, I think UVB can do it, but I think that this wiki source, I think, is kind of off here. I'm fairly certain that it's actually UVC that we generally think of doing the thymine reactions. There's a few reactions. This is one of the primary ones that occurs. So anyway, essentially we get this dimerization where we have two thymines together next to each other, and then they dimerize, so they kind of cross-link like this. Then whenever it's going to replicate or split or whatever, it really prevents the procedure from occurring in the intended manner. So it won't be able to do that potentially because of that dimerization. So then, if we get into it, then you could also look at repair mechanisms would be targeting those dimerizations to aim to fix them, to remove them and to repair them. So another possibility, and this is what I think is going to be the more often or the more likely UVB inactivation or disinfection mechanism, would be endogenous ROS. ROS being reactive oxygen species. So, and endogenous meaning it occurs or is generated from within, right? So we're producing these reactive oxygen species from within the cell because there are different molecules that what we would call are chromophores. So a molecule that has some chromatic or light absorbing property. Certain molecules, when they absorb light, will then get some sort of excitation, and that excitation then can lead to the production of reactive species. A lot of times that's going to be single oxygen. That's a pretty common one. There is potential to form hydroxyl radicals, which are extremely reactive, or superoxide radicals, or peroxides of some sort. So there's a few different pathways that can happen. You generally need high energy light. The light that we're receiving right now is very few molecules that could absorb our visible range light and make excitations of this level. And you actually have to have a certain energy level threshold to make make each of these reactive species. Single oxygen you can do with the right molecule with visible light, but it's not super common. Hydroxyl radicals, there just is not enough energy in the visible light photons to have the chemical reaction necessary to form them. There are some limits, and that's why we consider that if we're going down to UVB, that could certainly happen. This is the type of damage that these reactive species can then react kind of anywhere with any molecule or bond that is it can oxidize, and then you're having these oxidation reactions that attack your DNA or your other molecules. This is why ultraviolet light can be carcinogenic in that sense. It's more so than just the dimerizing the points of DNA, which I'm not sure, maybe that's carcinogenic too, but this oxidation, we know oxidation pathways, we like to eat antioxidants for this reason, right? We want to reduce the amount of random oxidation occurrences within our body because they can cause mutations, and who knows where it's going to end up. So an antioxidant then is something that reacts very quickly with these reactive species so that they're less likely to react with important molecules in our bodies. So that's kind of the role of antioxidants, and that's, in a sense, that's how we detect them, is putting some chemical that we can observe and seeing how quickly we're degrading it in some experiment. Okay, so that's kind of why we get sunburns, is these oxidation processes causing lots of irritation, lots of damage, in addition to probably some heat stress as well, given just the amount of heat. When something is hit by a photon or absorbs a photon, there is some level of heat that's lost. Even if you have some sort of photochemical reaction, you might see like a ground state up to a singlet excited state for some molecule that's now excited. And if it's the right kind of molecule, maybe it is like a phosphorescent molecule or like glow in the dark sort of thing. It can form like a triplet state and be excited. But anytime you excite it to some level and then it kind of relaxes back, there's heat lost right there, and then there'd be heat lost in this transfer, and then eventually, if it's a photon or if it's just relaxing back, whatever, or if it's just going straight down from here back to the ground state, then that's a lot of heat lost. Okay, so even if you're doing like fluorescence or phosphorescence, there's still heat loss involved and a photon emitted, and if not, there's just heat loss in general. So there is a lot of heat involved with the photons just being absorbed. Anyway, so a couple reasons for sunburns there. So I wanted to kind of take a look at using different, or I guess new sources of ultraviolet. We mentioned the mercury fluorescent lamps. LEDs are really coming online now with different technologies, different applications, because we can use an LED for a different form. We can put it into different forms. We can make use of it in a few different ways, and we'll talk about why UV transmittance may be quite improved by using a slightly different wavelength. So here's an example. There's a company called Aquasense started making small devices. Here's one that's kind of an inline treatment system. You have it maybe in your home or something, or at a tap, and you provide it power. It's got kind of a fan for a heat sink here. You're running the water through. It probably circulates through once or something, and then back out, and it's being exposed to a UV LED in here. So it's a very small unit, and that kind of is transforming the options in some way of what we can use. So kind of just one more graph here, kind of showing the same stuff we were looking at. The green line is sort of the germicidal effectiveness typical. And one of the advantages an LED can provide above this mercury emission we see here is that we can target that absorption spectrum a little better. So that's one thing. If we can have just more of the photons are being absorbed by DNA, that means we have slightly more effective action. But another thing that we can take a look at is really the light attenuation through the system. So you're probably familiar with the Beer-Lambert Law or seen it before. Certainly in general chemistry, you were introduced to this even if you didn't realize it. This is just the law that's saying light through some media is going to be attenuated. Light through the atmosphere is attenuated, light through the ocean is attenuated, and eventually gets really dark. Light through a solution with something that absorbs that light is going to attenuate, and it's going to do so on the basis of how much light is being absorbed. And so we have this law then. Our transmittance, we can call it, is I over I naught, so the intensity we observe coming out compared to what we started with. We can describe the absorption then, how much light was absorbed, A, as the negative log of the transmittance. And we can define that as A equals this epsilon, which is wavelength dependent molar absorptivity coefficient. So you'll probably see this value on papers sometimes if you're looking at anything that's related to photochemistry or to just light absorption in general. It doesn't have to be photochemical. But essentially this, you'll see plots sometimes with molar absorptivity coefficients. This is on a per molar basis for a centimeter, standard cuvette centimeter. It's how much light is being absorbed. So it's a pretty common metric. And so it's essentially saying the absorption is that coefficient specific to the molecule times how long your cell is. So you see this the beaker here we have, this graduated cylinder here, we have some depth to it, right? This would be our path length, or in this case our B. So you may have seen this written as path length instead of B, but in either case, you can see this light from the laser pen is going through a set distance. I think it also looks like it happens to be fluorescing, going from green to yellow, but you can see how it's attenuating through it. And so if you were to look at just 1 centimeter or something, you'd still have some light coming through the other end, right? Okay, so then C finally is the analyte concentration, and this is really the premise of a lot of our basic analytic methods. How we have this direct concentration dependence, at least in some range. We can make a standard curve with a UV vis detector saying, okay, how much of this dye is in here? We dilute it by half. We get half of the amount of light absorbed. You know, it's a very robust standard metric. You've done it before, and it's quite useful. So the same stuff applies when we're dealing with UV application to treating water, right? We have water. Stuff in the water is potentially absorbing the UV, maybe the water itself, perhaps even dissolved oxygen in the water. If we're ozonating, ozone will absorb. We know the ozone layer protects us from UV, so if you think about that, we have UV absorbing our radiation. And speaking of that, if I were to shine a UV lamp right here at you, you probably wouldn't be receiving much of it. Well, Ian and Wei Liang maybe, but not a lot, right? And at least you've got glasses on, and that would probably stop it. Ian, you know, I'd be screwed, and maybe Ian too. That would help. So I would just be the problem one. But if I put it behind this, that would actually absorb all the light. Almost all plastics absorb UV. Almost all glass does. You have to have specialized quartz glass or specialized something to have transmittance through it at the UVC range. Now UVA, a lot, not as many glasses or plastics absorb it. Some will, but if you ever look at sunglasses that you want to buy, they'll probably have some sort of UV rating, and it'll let you know that, oh, it absorbs this amount of UVA or UVB or whatever. So just something to keep in mind. But if we take a look at how much absorption the atmosphere does when considering ultraviolet light, we have here a scale, and if you remember, we have from here to about here, we call this the vacuum UV range. And then from about 200, maybe if we define it a little different, somewhere around 180 to 200, we say this is up to kind of 280. This is UVC. Then we've got UVB, small portion there, and then UVA, up till visible. So if we consider this and then look at it in reference to where ozone and oxygen absorb light, we see the role of the ozone layer. So it's kind of a strange graph, and I'm not sure. So I'm not sure quite what it means, absorption cross section. I guess maybe this is for the atmosphere itself. But what we see is essentially ozone is absorbing everything from even into the UVA range all the way over to, and very strongly into, that UVC. So the ozone layer then is serving us very well by absorbing a lot of that energy. And by the way, what's happening in the atmosphere is we have ozone being struck by the UV, and that's causing different photochemical reactions. So up in the upper atmosphere, and even in just the atmosphere in general, as it's receiving all this light, we're getting all sorts of radical chemistry occurring. So things like an oxygen radical plus an oxygen molecule, so O2 and an O dot. Things like that, I might not have the exact mechanism right here, but then you have all sorts of additional reactions, and if you get water involved, there's ways to get that hydroxyl radical. In atmospheric chemistry, that's known as the atmospheric cleansing agent. Very small amounts of it exist at any given time, but it's constantly being produced and constantly being reacting with stuff. So that's one of the ways you would convert from methane to CO2 over time in the atmosphere. You've probably heard of methane as a greenhouse gas, CO2 as a greenhouse gas. Methane is more potent, but it turns out that oxidation reactions like this with hydroxyl radicals end up converting methane into CO2 over time. It takes, the typical lifetime or half-life, I guess, of methane, I think is about 15 years, whereas CO2, the typical lifetime is on the order of 70 or 80 years, and that's partly just the transport back into the Earth system. So anyway, all that's happening, and that's going to be happening in our water, perhaps to a greater extent. We can also see the oxygen here. This one, oxygen is absorbing here. So it doesn't look like much, but in practice, like I mentioned earlier, if I were to be shining a light, and I know this just from playing around in the lab and checking to see, okay, are we safe here? And done it in a safe manner, but just taking a UV radiometer and checking, are we seeing emission here? And maybe, okay, I know the light attenuation from this distance in my photoreactor, but what happens if we move it? Done some experiments like that. And you can really see that oxygen, we have a lot of oxygen in our atmosphere. So even though it's not absorbing a ton, and it probably kind of tails here, at 254, there's so much oxygen that light would certainly not reach the end of this room unless I was really blasting it with a huge amount of UV maybe.
Especially here in Louisiana, there's a lot of water in there. And the water doesn't really absorb UVC very well, especially pure water, but it scatters it.
Yeah, so you could certainly have light scattering as well.
And there's particles and stuff making it scatter all kinds of places.
Yep. The other thing you want to be concerned about if you're blasting lots of UV is potential to form ozone. So one thing you can think of is you can split oxygen into I don't know if it would be two like this, or I guess that would probably be what it would be.
It splits water. It splits water in the
You can potentially split water,
yeah,
but one thing that happens in the atmosphere as well is you do form ozone from oxygen,
yeah.
and vice versa. There's cyclical and stuff, but the point being, if you have a strong UV source that you're using in a facility or in a lab, you actually do want to be concerned, because you don't want to generate a bunch of ozone and then have people exposed to high ozone concentrations by accident. So when I've been hearing for the past year all these discussions about, ultraviolet light this for coronavirus, let's put it indoors, let's put it in our HVAC systems, I'm thinking to myself, are we taking care that we're not adding a bunch of ozone? That's a lung irritant, we ought to consider, if we are using these new 222 wavelength guys, that's going to create a lot more ozone than a 254 lamp. And so let's at least be mindful of that and consider it as we're designing our UV controls. So that can eventually go to ozone. And I'm I'm sure these are not correct reactions here, so don't take those as the actual ones. But point being, you do create ozone, and it's photolytic reactions. There's intermediates and stuff. We could take a look at. Okay, so another thing, now that I've got all this written on here, one thing I wanted to show you was just kind of a fun thing that we did back when we had the solar eclipse here. We had a brand new radiometer, and we took measurements of the solar eclipse as it happened. So these are measurements just from right across the road here outside of our lab, and we could see this is the solar spectrum over time during that eclipse. We're not expecting much to happen aside from just reducing intensity as the eclipse happens, right? And this is a partial eclipse, so you can actually see the different bars here. It's like at 1220 and then 104 and so on. And so it goes from here, it lowers, and then starts climbing back, I think. But the point being, this lowest one, that's the eclipse. And what I wanted to show you was the UV vis spectra, because the sun is putting out lots and lots of photon energy, all sorts of wavelengths, including gamma rays, X-rays, UVC, vacuum UVC. But the reason we call that vacuum range is because there's so much absorption by atmospheric stuff, oxygen in particular, that you need to apply a vacuum in order to get it to actually go through any reasonable length of distance, right? That's why we call it a vacuum UV. It's not really applicable outside of a vacuum situation. So just wanted to show you that, at the kind of strongest intensity, this is that UV range, and that was, I think, September or something. Was it September? I feel like it was fall sometime, 2017. Might have been the spring. I think it was early fall 2017 that it happened. Anyway, so that's the amount of, compared to the amount of visible light we're getting from the sun. That's a kind of taking a look at the amount of UV, and you can see that it really does tail off. It's getting kind of close to UVC range, but if we were to add metrics there, this would probably be the 300 mark. So it really does just tail into the UVB range, but most of the UV that we receive is UVA. So just kind of wanted to show that, see what that looked like, see that light attenuation, because maybe there's some difference, but you'd expect that it would look something like this in terms of the total emission from the sun, with the amount of energy being put out by all the different reactions that are happening there. Okay, so wanted to take a moment and describe a couple of the different application techniques for traditional mercury-based lamps. There's a YouTube video, somebody actually, he happens to say he's in Louisiana somewhere talking about it. It's not a particularly high production quality video, but it is kind of an interesting topic here, discussing the difference between a contact lamp versus their company's new technology, a non-contact lamp, where a contact lamp has a lamp inside the water, and water is just flowing past this lamp, and it's inside a quartz sleeve to protect it. The quartz sleeve is fragile, the lamp is fragile, and has mercury in it. So we want to be careful with both of those. That quartz sleeve, it gets a little bit hot given that it's got the light source right next to it. It's going to get dirty. It's going to accumulate stuff. It also tends to be negative charged. So it's going to accumulate junk on it. You have to clean it. You're going to have to scrape it probably. And you're going to want to be careful when you do that, because it's expensive, because it's this fancy quartz, and it's fragile. So it's not a great situation. And as this guy talks about, practically you have to have the infrastructure in place to hoist these out of the system. You typically have to put these in like a trench system for the water to flow through. So it's, I'll play it for just a couple minutes. It's like a 20-minute talk. I don't even think I listened to the whole thing, but it's kind of interesting if you wanted to, if you were interested in taking a look. And what he's comparing it to is a kind of their new technology where they were able to make it plastic that had enough UV transmittance to make it worthwhile. And I think he said it was activated fluoro polymer of some sort. So it's kind of like PTFE or something, where it's fluorinated something, and I don't know the exact chemical makeup, but essentially what they're doing is then having that plastic casing that the water is flowing through, and then have the lamps around the outside shining into it through there. So you're getting some loss there, attenuation through that plastic, the pipe, but you don't have to worry about cleaning the quartz. Presumably that plastic, you can just replace that tube if it does get fouled up. Probably has different properties. It may not have a charge at all, so it's going to be maybe like non-stick coating, which would be great for fouling purposes. So that's this link here. The same links on the previous page as well. So I'll just pull that up to show you real quick.
For inviting me. We're going to talk about.
Of course, I probably don't have it playing the sound.
How it relates to what you probably haven't been exposed to, traditional UV, which is quartz-based systems.
So I'll just do like 3 minutes.
Can everyone hear me?
Show you.
Great. So for 50 years, quartz-based UV has been used in wastewater treatment applications, and it has a lot of issues. It has lack of performance, high maintenance, high replacement costs for spare parts. Non-contact UV has eliminated all the maintenance and improved the performance for wastewater treatment. So UV can be used in any wastewater treatment format: SBRs, trickling filters, lagoons. Down here in Louisiana, UV has probably not a good name for certain applications, especially when you get into lower UVT water. In municipal applications, UVT is 65 as the baseline for design.
So he's talking about transmittance.
UV can go down to 40 UVT, so lagoons are good applications for contact UV. So if you're planning to use UV or you're using UV, what are the characteristics experienced with standard quartz-based systems? Difficulty to maintain and clean, performance, expensive to operate and maintain from the energy costs, time-consuming and messy wet lamp quartz sleeve and seal changes because it's submerged in the effluent. If you need to work on it, you need to bypass the system or have a second system and a separate channel, so you still have disinfection and an expensive replacement parts. And cleaning requirements. Quartz-based systems can have manual cleaning, mechanical devices, either pneumatically driven
So it shows an example.
So contact UV requires gates upstream and leveling weirs downstream, making more expensive installation, bigger footprint, more civil work. You have quart sleeves and seals to replace.
So you just mentioned that they require control of the flow, and that's because they're using the water itself to cool the lamps. So you have to maintain the right level of water. If you had some sort of change in the flow rate for whatever reason, you don't want the lamps to get too hot and burn out. So that's one of the challenges there. You don't have that same challenge with the other system. Right now, he's just going to show kind of what the quartz looks like, and
Hide the quart sleeve, you seal it, you submerge it in the effluent in this orientation, or it can be in this orientation. So the physical characteristics of quartz 2 has a negative charge. So when you submerge that into water, put a hot lamp in it, anything that's positively charged left in the effluent flakes out on the quartz 2. And over a period of time, you have maintenance issues to keep this clean. So squeegee fails, or you can't get the boundary layer off. Now you have to lift that lamp rack out, acid wash it, take the unit offline, then put it back in. So it can be. That doesn't sound like fun.
okay. Oh, actually, I think he's.
If anyone here has ever done that, you know it's not a good.
Or it was already broken.
It can be time consuming. I know guys that clean acid wash about every 3 weeks. Takes 2 guys 8 hours. So
It's a lot of time.
uses an AFP tube that's non-breakable, lasts the life of the system, you never replace it.
I know.
And the lamps are always dry on the outside of the tube. So for easy access, we don't have to overcome any of the water conditions.
So that's kind of cool. That's mercury based. I think that similar technologies or applications will show up with UV LEDs. I think he might. No, it's been a while. I did watch through this the first time I went through this, but I didn't rewatch it this time. I think that that thing that was on the desk in front of him was kind of pilot scale system that he had for demonstration. So that's kind of cool. That kind of gives you a little more perspective on what it takes to operate UV. He was dealing with UV for wastewater. That's very common, but UV is also used for drinking water applications as well. And so he was talking about UV transmittance, and I mentioned earlier one more reason why UV LEDs might kind of take the cake in terms of the market. So if we look at 254 nanometers here on this plot, this is the absorbance values for 2 different natural organic matter samples. So we've got Suwannee River natural organic matter, and then some other river natural organic matter. And the point here is that random organic matter in your samples, whether that's natural sources from here, or maybe it's a wastewater effluent's got a bunch of junk in it, the UV transmittance is going to be relatively low through the water. Like that laser pen picture that we saw, it was not transmitting more than a few centimeters through that liquid because it was full of this dye or whatever. So you can imagine high strength wastewater is going to be the same deal. A lot of organics. That stuff absorbs, especially in the UV. Now, visibly, we maybe only see a little tint of a brown or greenish color or something. In the UV, there's all sorts of molecules that are absorbing. And so if you take a look at this, would be our typical 254 mercury emission, something like that. Then you can compare that to maybe tuning even just like 20 nanometers different. You're still in the germicidal curve, but you're at like 280 or something. You can see that difference between this much absorption versus this much, and depending on what type of organic matter you've got, that can actually be a pretty good improvement in efficiency, just because you're having more light transmission through the system. So I expect that's going to be another advantage realized by UV LEDs. Okay, so we got through everything I wanted to say in perfect time. All right,